First, I'd like to organize whole kind of invitation. It is really great back to be KITP. So today I'd like to talk about our recent work on entropic derivation of g-theorem and its connection to holography. And this talk is mainly based on this paper, which we just submitted recently. It's Jonathan Harper, a postdoc, and our graduate student, Hiroki Kanda, and Kenya Tasuki. And also, in the end of my talk, I will also mention our other recent paper about which constructs some explicit example of the boundary RG flow in the context of ADS-CFT, especially using ADS-DCFT with localized scalar, and also it's somehow connection to holographic, somehow entanglement phase transition. Okay, so let me start. This is the introduction. So entanglement entropy provides a universal measure of degree of freedom of quantum field theory. It's quite universal. For example, if we look at some, this locality of quantum field theory basically leads to area law of entanglement entropy. So in Bombelli et al. And also Seredoniki on this paper, first find this area law. And also if we look especially the quantum critical points or conformal field theory, so entanglement entropy gets divergent because of this critical nature. And it has a very nice universal scaling in terms of central charge. C is the central charge divided by 3, and log of A is a subsystem, size of subsystem to define entanglement entropy. I'll come back later. And epsilon is a UV regulator, first found by Holzer, Larsen, and Wilczek. And also, there is a very fundamental inequality, which I will explain later, and plays the most crucial role in this talk, called strong subjectivity, which is some kind of generalization of second law of thermodynamics. That gives a basic theorem in quantum field theory and the RG flow, like C theorem and F theorem, owing to this very beautiful work by Cassini and Feld. And also, from the viewpoint of gravities, by using ADS-CFT, we can actually understand entanglement entropy, a kind of measure of size of the universe. I mean, more precisely, minimal area surface or extremal surface area, but that's basically measures size of the universe. So based on my work with Shinsei and also Veronica and Mukun here. And so that suggests also from the gravitational viewpoint, it's like some maybe quantum information is some origin of the universe, like it's from qubit. But of course, this conference is string theory and many string theory, I think, believes that it's from strings. So that suggests maybe qubits and strings might be somehow closely related. But this is a huge, really big goal. So before that, I just want to, this talk, I'd like to more focus on this basic nature, so, and connection to the RG flow of this entanglement entropy, using entanglement entropy. So this entanglement entropy, we already have a nice talk by Jonathan yesterday. But here is, I'm really assuming, so type 1 on my algebraic viewpoint in recent understanding. So we have some discretization of this quantum field theory in terms of quantum manifold systems. But so we assume some Hilbert spaces factorized into A and B, and we define reduced density matrix just tracing out B. So this is a size of wave function, ground state wave function example. And trace out, and we can define entanglement entropy as usual. It's a von Neumann entropy minus rho log rho, rho A log rho. So this is a definition of entanglement entropy in this talk. And also, we can take some, in principle, take some continuum limit, epsilon goes to 0, but of course, this is a very subtle issue, and we need some von Neumann algebra and so on. But always, in my talk, I'm assuming some UV cutoff epsilon, so just using some more kind of traditional way of treating entanglement entropy. So I'm not getting into this von Neumann algebra thing. So, but anyway, so the most crucial inequality, which plays a crucial role in my talk, is strong subjectivity. So this is first found by Limp and Ruskay quite long ago. So for that, so this inequality called strong subjectivity. And for that, we decompose Hilbert space A, HA, HB, HC, and also some other parts. So A is, there are no overlap between A and B. So in the spatial reasons, this is a time slice of quantum field theory. So we can just decompose Hilbert space, just cutting space into A, B, and C, and other parts. And then this whole entanglement entropy, which is defined by, for example, SAB, that means we trace out other part other than AB. And this is the entropy for that. And this is the entropy for BC. This is always, if we sum of this, it's always greater than these guys, SABC plus SB. And here SAB means it's a union B. So this is actually one of the most fundamental inequalities satisfied by entanglement entropy. And roughly speaking, it's kind of analogous to a second law of thermodynamics, which also we know is very important. And how to prove this? It's one systematical way to prove strong subjectivity is to use monotonicity of so-called relative entropy. Relative entropy basically measures the distance between two different density matrix, rho and sigma. This is defined a little bit not symmetric way, but this is quite useful quantity and always bounded by 0. And this has satisfied monotonicity when we coarse-grain some information. So, for example, if we trace out C, so we can consider this kind of combination, rho ABC and rho A times rho BC. And if we trace out C, so it just becomes rho AB, and this becomes rho N. And this inequality is just follows from monotonicity of relative entropy. This is just a mathematical equivalent to this statement. So this is strong subarelativity. So a main part of this, my talk, is to use this strong subarelativity and apply to many different setups in quantum field series. So here, first, let me start with this Cassini-Freitas proof of this entropic C-theorem. So this starts from strong subarelativity, but let's rewrite this into the following form. So I just call AB is rename it to be A, and BC is called B. So that A and B has some overlap region. So this is an overlap, and this is a union, sum of this, and this is just ABC plus SB. And we consider strong subarelativity, we apply strong subarelativity to two-dimensional, 1 plus 1 dimensional relativistic Lorentz invariant quantum field theory, but not necessarily conformal invariance. So because we are interested in renormalization group flow, so we start with CFT, but we can perturb by some relevant operator. So we assume Lorentz invariance and translational invariance as usual. So we look at ground state, but not necessarily conformal invariant. So, but the Lorentz invariance allows us to boost subsystem. So we can, this is a time and space, but we can define this Hilbert space decomposition like the other region and also this region, but we can slightly boost subsystem, and we call this is A, and this is B. So this is a black line, tilted line, this 45-degree line is a narrow geodesical narrow line. It's a right direction. So always we have this right direction. So, for example, if we take A union B, so this A is this subsystem and B is this tilted one, but then this, if we look at this line, this interval, so always it's, if we send some signal, always it's intersect with either A or B, always. So that means this is a Hilbert space for A union B. And if we take this one, this small one, then always the particle which passes through this line, this interval always intersect both A and B. So that means this is the A union B. Sorry, A cap B. Sorry, intersection of A and B. So, and we apply this strong subarelativity to this setup, then we can get some C-theorem. That's the thing. I quickly review it. So, in my notation, the absolute value of A means just Lorentz invariant length. So this is a Lorentz invariant. It's real Lorentzian time, and this is space. And then this very elementary but very important geometric relation is that, so this length of A times length of B is the same as length of these two intervals. And to make everything simple, let's take this AB as symmetric, the same angle. So that length of A and B is the same. Then it is, let's rewrite this length of A union B as exponential x, and A and B intersection is exponential y. Then obviously, because of this relation, and these two, because of this relation, A and B are the same, so we can identify it's like exponential x plus y divided by 2. Then strong subarelativity, an entanglement entropy is just function of x or length because it's Lorentz invariant and translational invariant. So it's just very simple functional, S is entanglement entropy, just very simple inequality, and this is obviously, this says that this function is concave. And second derivative is non-positive. And then, but here we'd like to define sort of some C function. So this is called entropic C function because it's defined from entropy. And we regard this subsystem size as energy scale, because this is the only scale which we probe this entropy. So we define this effective central charge or a C function in terms of derivative of S, because for two-dimensional conformal field theory, as we also just mentioned before, the well-known fact says that this C over C, 3 times log of length divided by epsilon, will be cut off. And that means if we take derivative of X, then it just gives C as a fixed point. So but this is, now we are interested in the theory, is not scaling, not conformal invariant. So this is deviates from central charge, but we can call it a C function because it's, as a fixed point, it's coincides with central charge. And then, because we said the second derivative of S is non-positive, so this derivative of C is also non-positive. And that means effective central, C function decreasing under RG flow. So this is this Cassini-Freitas entropic C7. So what we would like to do is to exactly the same, this kind of derivation by using using only strong relativity to derive g-theorem. G-theorem is a kind of monotonicity of RG flow, but which is localized on the boundary. I will explain later. And so I just finished the introduction, so I'd like to give new entropic g-theorem. And then go to some, these are holographic interpretation using some ADS BCFT construction. And also, finally discuss some explicit example by using boundary localized scale. So this is a BCFT. So we are considering some, so CFT is, of course, we have symmetry, Virasoro symmetry, left moving, chiral and anti-chiral. But if we have some boundary, so we are interested in conformal field theory, two-dimensional conformal field theory lives on, for example, upper half plane or a right half of the plane, like this. And there is a boundary, always I'm putting boundary at x equals 0. And there is a complete reflection, and we impose some boundary condition. And then we see that only one linear combination of Virasoro algebra is preserved. And in terms of, if we look this x direction as a time direction, so it's like a double weak rotation, then this looks like a quantum state, some state, this is called boundary state, and it satisfies this Virasoro condition. So this is a fixed point. So this at the boundary, this preserves half of the conformal symmetry. So this is we think this is a kind of boundary of course conformal invariant, so it's like a BCFT. This is a fixed point, but we put some, we put some boundary perturbation, it's given by some relevant perturbation, then breaks conformal invariant, boundary conformal invariance, and then we have a renormalization group flow at the boundary. But always we don't do anything at the bulk, so that means bulk is conformal invariant. This is our setup. But then, so this quantity, very interesting quantity called G function, is defined for can be introduced as follows. So let's fix some. Let's assume some boundary conformal invariant point. So this is considered by Affleck and Udoi, and then this quantity is claimed to be monotonically decreasing under boundary RG flow. But let's assume everything is boundary conformal invariant point. So there are 3 definitions, and they are equivalent. And first one is just we say that compute disk amplitude with some boundary condition, with some conformal invariant boundary condition. It's of course alpha is alpha levels boundary condition, and it's a result of course partition function depends on alpha. But anyway, let's call this a G alpha. This is a G function, but we take a log of this. This is called boundary entropy. So we often take a log. So let's call this log G as a G function. This is one definition, and this is almost trivial, but we can consider seeing the amplitude, and we can, so this is a boundary state here, and we take our L goes to very large. Then on this cross string like modes is, it's a long distance, so it's only lowest energy excitation is propagating, so it's like E0 is the lowest energy, and we can have a 2 disk contribution factorized. So this G also can be read off. Can be formed with. This is quite convenient because this is already normalized. So boundary state has a nice normalization because of open closed duality. So, and for this one, first one, we have to regulate. In general, this is divergence, so we have to regulate. But this one is somehow normalization is very clear. But these two are obviously equivalent. But also, interestingly, so this quantity appears in entanglement entropy as first found by Calabrese and Cardi. And so we consider some left half plane, for example, our right half or both are fine, and we take a subsystem A to B so that it starts at some point to end on the boundary, or end of the boundary, and the other part we call B. So entanglement between A and B, quantum correlation, is computed by entanglement entropy, and there is a well-known result, and that we can derive very easily by using replica trick. We can put some twist operator here. There is a logarithmic term, but C over 6, not C over 3, because it's only half, right? You can imagine some Miller method that gives C over 3, but we have some half of that because we have a left half, only left half, and it's like length over epsilon. So if we take a Miller, it's like 2L, right? 2L over epsilon. And also there is a finite constant contribution, which is turned out to be this log G, like a G function. And so we can read off this G function by looking at this entanglement entropy, and we are going to mainly working with this entanglement entropy to see this monotonicity. Okay, so this G-theorem, basically, so now we go to G-theorem. So we are now, so far we assume boundary preserve conformal invariance, but now let's put some relevant perturbation localized on the boundary, so then we have a boundary RG flow. And in that case, African and Ludovic claims that there is a G-theorem. So it's like a C function. There is a G function, which is actually identified as this boundary entropy. It's monotonically decreasing under boundary RG flow. And G function, already we mentioned, it's like originally defined as a discompute, regularized disk partition function. And so we put some relevant perturbation O, and we take this localized at x equals 0, and do some boundary RG flow integrated dt. And this G-theorem itself is proven, especially for a more standard field theoretical proof is given by Friedan and Konecny. And also later Cassini and Trova proved this G-theorem by using more quantum information theoretical way, but especially by using relative entropy. But in both of this proof uses this real RG flow. It's a RG flow, and for example, relative entropy compare this RG flow state and also the state before RG flow. But here, this proof originally, if we go back to this original entropic system, points that we are changing this size, subsystem size, and regard subsystem size as a effective length scale. Then, so there are no proof has been known. And we gave actually that proof, and this is a kind of third proof of G-theorem. And it's, even though this is a third proof, but I think it's quite useful because it's just purely geometric, right? Like this one, like this way. So we can see this quite geometrical nature of G-theorem. So that's what I would like to give first. And that's actually the main point of this talk. But here already mentioned, but if we have some, for example, this right half plane, and we define subsystem A is here, and let's take this length as L. This is the subsystem A, size of A is L, capital L. Then we know this results. And, but still we can have a similar behavior, like just this a constant, some constant, no divergence, but this divergence is always logarithmic. So we can always have this kind of form, even though log G is no longer, it's like no longer invariant. I mean, log G in general depends on size of L in some non-conformal case. So, but in conformal invariant cases, this log G doesn't depend on L. So this L depends only here, but in general, log G depends on L. But so we'd like to say that this log G as a function of L is a probing scale, is always monotonically decreasing. And this is an entropic G-theorem. So that's what we want to show. To show this, there are some tricks, two tricks. This is actually, but it's not very elementary, but it's somehow very important. First one, this only, both are only arises in the presence of boundary. So if we have some boundary, the entanglement entropy for this interval is equal to this interval. This difference is just the end point is different, but there are two end points, and one end point is the boundary. They are different, but the bulk end point is the same. And of course, it should not, I mean, more than, these two should be, of course, space-like. And because if we take some mirror, for example, mirror of this A and the mirror of this guy, both have the same domain of dependence. And or in other words, if we send some particle, it's completely reflected back, it's completely captured by A prime. So that means SA prime equal to SA. So we call this, and only that means only fixed by this length between this point and this boundary. So boundary between the distance between boundary and this point, this is called capital L again. So this we call this quantity as disconnected entropy because it's become related to some disconnected geodesic in the holographic description. And then also another point, this also looks trivial, but this is actually quite important. So we have some boundary. In general, this violates translational invariance. So if we take some 2 points in the bulk, this is so 2 points in the bulk, this is no longer simple. It looks like very complicated. But especially if we take the limit where this, originally this is of course space-like. Always subsystem should be space-like, but let's take a light-like limit. Then we have a universal answer about behavior. This is just the usual entanglement entropy, C over C and log of L over epsilon. L is, of course, is invariant length. And it is also easy to confirm this in holography, but also from quantum field theory because it's, distance is 0 because it becomes null. That means we should contract these two guys in the OPE. So then this result, I think, is quite obvious. So we use these two facts and apply strong subjectivity. The setup we consider for this strong subjectivity is this one. So we have a boundary here. We have a boundary, and this is we consider the VCFT is defined here. But we take some, this is a right-like direction. These two are both are right-like direction. And we take some subsystem A and B like this, but no longer it's symmetric. We should take some special boosted limits. So we take this point is UU and it's S, and we take this, we have some flexibility to change these location of this point. That's fine. Still, we can put this A and B, and this is union, and this is overlap. So we have so many parameters here. But for this entanglement entropy, so A and also A union B are also both ends on the boundary. So this is only function of this x coordinate, so S minus W and to S minus B. But the other guys, like this guy, A cap B and also B, is a non-trivial. It looks at first sight it's non-trivial. It's both depend on the two end points. It's a bit complicated. But to simplify calculation, we take first we take a right-like limit that U gets very close to S. Then this subsystem B and A cap B becomes right-like, gets very close to right-like. Then we can use previous fact that we can simplify, and we can basically predict the form of entanglement entropy, and that gives this kind of result. Yes. Yes, that's right, exactly. It doesn't depend on the, where it anchors the boundary.
If you shift the point of the boundary, then it will change as a function of time or not?
Sorry, what I mean this one. So you can change this location, but this bulk point should not change.
I see. So in general, things can depend on things for space-time in terms of the bulk, but you're saying if you change this location, it doesn't change because of the...
Yeah. Yes. Of course, we assume time translation invariance because we are looking at transit. So, yeah, thank you for the question. So these two guys are very easy to calculate. This is the first point. Yes?
A question about this point. So,
yeah.
In principle, could you have a finite piece? Because when you're doing this, you're doing an OPE between two twist operators. And so there could be some operator, the right-hand side, that has a non-trivial value.
I think that, it's like, it's not finite. It's like, I think, multiplied epsilon. Also, we can confirm this in holographic calculation. But because also in the holography, it's very approaches to the boundary, so minimal surface gets close to z equals 0. And that case, I think we have epsilon times something, such a contribution, but finite contribution is not.
Just to clarify that the nullness is only up to the cutoff here, so its proper length is still above epsilon.
Yeah, that's right. Yes, exactly. Yeah. We are not taking strictly zero, but yes.
Maybe the constant is cancelled between SA,
Sorry, okay, yeah, it counts. But I think that as far as I see holographic calculation, there are no finite piece. Because it's a logarithmic. Yeah. And then we simplify this delta S, SA plus SB minus SU like this. And then we know these two guys, like this guy and this guy. And it's like given by this log. And there is a SA and, SA and also SA cap P, and that gives this disconnected contribution. And then we can, so that's still a bit complicated, but we can take further limits that B equals to W, B is very close to W, so that these two guys are very close to each other, and we can take some Taylor expansion, and then this is strong subjectivity, delta S is greater than non-negative, leads to this bounds. But still, this is not completely enough. So, but the point is that L and S, we can choose any value. This is a flexibility of this setup for any L and S. So we can assume L is very, very large, much larger than S. Then we can say that most strict bound is C over 6 we get from this equation. And then we introduce, so this is an obvious thing, but we introduce this entropic G function, disconnected contribution minus this logarithmic divergence, which we know very much. But still there are non-trivial L dependence. And then this strong subjectivity equality is just translated into this entropic G function, entropic G-theorem, like this way. Okay, so this is anyway basic proof, the derivation of this entropic G-theorem. So we can also generalize this idea to the case of interface CFTs. So interface CFT, so we have some conformal field theory on plane, but we can put some line defect which preserve conformal invariance. In that case, it's interface CFT, but in general, we can turn on some relevant perturbation on this line. That gives some non-trivial renormalization group flow, but still, in that case, we have now C over 3 entanglement entropy for region A. So let's take this length of A is L. Then it looks, there is some contribution, finite contribution. So, but the point is that we always assume this subsystem A is symmetric. These 2 points are just symmetric. It's a mirror image. Otherwise, its definition is a bit ambiguous. So always let's take a symmetric point. But then, so actually previous derivation of entropic G-theorem can be applied here because we can just double copy of this triangle and just call this A, B, A1, B1, but also A2, B2, and just take a union of A1, A2. So that means this equivalent to this Cauchy, this inter. And that gives this one. And another one gives this another D function. But also, again, we have a tilted one, and we can get rid of that by taking another limit. And then, so this strong subjectivity gives again this renormalization group flow, also monotonicity over G. So there are also recently very interesting work by Karuchi and Kusuki and Oguri and so on about this more general interface CFT where central charge plays very important role. But here, much simpler. Here it's much simpler case that everything is just homogeneous and central charge is just a single part. I mean, only one central charge. Okay, so these are, so far we discussed some conformal field theory or, quantum field theory approach. Now get back to, now come to holographic calculation. So here I'd like to talk about gravity dual of BCFT, but there are many approaches, of course, string theory, motivated one, supergravity one, and so on. But here we are we'd like to consider some simple-minded one. It's just hard wall approximation. in general, this is a kind of zero-solved approximation, but sometimes this becomes exact, especially in the case of if we put some Orient fold. But in general, it's, some model. But this plays very, this gives some quite nice result, especially for three-dimensional case. So this is this ADS BCFT construction is like this, very simple. So we have some manifold M. We consider some boundary conformal field theory on M with some boundary. And then we consider, and then gravity dual is given by just extending this boundary towards the bulk, like Q. So this is so-called n towards the world brane. If we just like E of W brane, there are nothing outside, and everything just inside. So claim is that this BCFT on M is just dual to this internal region surrounded by Q and M. It's called M. And this Q should be dynamical. So because there are boundary dynamics, that means instead of Dirichlet boundary condition, we impose Neumann boundary condition. So that is written very simply in terms of extrinsic curvature. This is usual term. This is also Brown-York tensor. But also there are contributions, sometimes contribution to some from this end of the world brane. We can put some localized matter here. Then TQ is an energy stress tensor from this localized matter. And so, yeah, so we just solve Einstein equation with this boundary condition. This is a basic setup of this ADS BCFT. And the case with some boundary conformal field theory, if we have some BCFT symmetry, we can assume this TQAB is proportional to HAB. Actually, in that case, we can show that this preserves boundary conformal symmetry. And in other words, there is just some constant. This is we call it tension. This tension of this end of the world brane. So T is an arbitrary constant, but there are upper bound. And in 3 dimensions, it's like just 1 over ADS radius. And then Neumann boundary condition looks like. And for this case, especially let's take a 2-dimensional boundary conformal, it's dual to 3-dimensional ADS, but surrounded by end of the world brane. So we cut out this region. This end of the world brane is now just a plane, like given by Z equals proportional to X, some constant which depends on tension. If tension is 0, this means that this is really vertical, and tension gets closer to 1, it looks like very close to the boundary. And of course, bulk ADS3 case we don't need to take into account back reaction, so it's just ADS3 metric, just usual Poincare metric. This is a very simple setup, but in general, we are interested in the case with the renormalization group flow. It flow like this way. So this line now is a little bit bent inside. So then that gives some non-trivial RG flow. So, but here in this setup, so how we can calculate entanglement entropy. So this is actually basically very similar to usual holographic entanglement entropy, namely that's given by some minimal area surface or extremal surface area. But there one very important new ingredient. So we have some anti-Doshita space here, and this is a boundary. BCFT lives here, upper half plane. And there is an end of the world brane, which extended from this boundary of BCFT. And the new thing is that this minimal surface or extremal surface can end on this end of the world brane. So we can think also this is some special case of this island calculation in terms of this brane, some gravity on this end of the world brane, assuming some brane world gravity. But here we just assume this relation between ADS and the BCFT. So if we have this setup, this is dual, claimed to be dual to this BCFT on the boundary, and we take some subsystem here. So this entanglement entropy of this case is computed by this way. So the non-trivial thing, so we should find the location B. Also, we have to take a minimization of against any shape, by deforming B and location B and shape of B and so on. In higher dimension, it's complicated, but in lowest dimension, it's very, ADS3 case, it's easy. That's what we do. But for boundary conformal invariant case, we have just plane, so we can calculate this length. Subsystem A is here. Then this length is, we have some, it's only attached at the boundary 1 point, so it's like C/6 divergence. And this extra piece basically gives constant part, depends on the tension. So if tension goes to large, then this extra contribution to be large. Right? Tension is sort of degree of freedom, and indeed that is related to boundary entropy. This part is boundary entropy. So this angle is basically degree of freedom, which is localized at the boundary. So of course this is what we expected, like this. And in this setup, we can basically discuss RG flow, but before that, so anyway, we are interested in strong subvolatility. So what kind of results can we obtain? So strong subvolatility in static setup actually trivial. So let's assume there are no time dependence, then it's trivial because minimal surfaces, so minimal surfaces are on the same time slice. Yes? Yeah, exactly.
Wasn't it the case that you do earlier that A was separate from the boundary where you were drawing these island surfaces? Here this A would again that's the boundary?
So you mean, so if you change this subsystem?
Sorry, I was just wondering, does the boundary does not require A to extend out till the boundary?
Yeah, this boundary term, this contribution, it's come from this extra piece like this part. So there is some horizontal line, right? There is a horizontal point. And this part basically gives first term. And this upper part gives finite constant. Yes?
What is the meaning of the divergence as the tension goes to 1?
Yeah, tension is bounded by 1. Because tension equal 1 means really it goes to the boundary. This end of the boundary constant is the ADS boundary. So it's a real upper bound. And if we want to go to larger tension, then we need to think about the logical brane rather than, this is an ADS2 geometry, but if you think DS2, then you can go, take a larger value of tension. Okay. So yeah, you can easily show that just the usual strong subvolatility in as usual ADS CFT, which might work with Hedrick, and also there is also further inequality like monogamy or mutual information by Hedrick, Hayden and Maloney, and these two are automatically satisfied for a static case. It's very easy to see. Essentially, proof is the same. But we are interested in Lorentzian case, so we are computing this length. So this is the end of the world range, this is the ADS3, and this is subsystem A, and we are computing this length. In general, non-trivial, but the ADS3 case, we can have a nice analytical control. So we are interested in this disconnected entanglement entropy. So these are some details, but in the end, we get this. This derivative is very important because we want to claim this is non-negative. Its strong subjectivity says that this is non-negative. And so this combination looks like this. Sorry, this should be smaller than 0. So this combination, and this combination is actually, indeed, we can show this strong subjectivity is satisfied. This is smaller than 1, non-positive. Then by assuming null energy condition of the brane, end of the world. So if we have some localized matter on Q, and if we impose this null energy condition, then strong subjectivity is satisfied. This is something analogous to the also work by Alan Gore about this strong subjectivity in Lorentzian ADS50, assuming also null energy condition. So that case, we also g-theorem also holds in this theorem. So this is a holographic counterpart of this g-theorem. Okay, so maybe I'm running time. So just I want to mention that. So we can construct explicit model of boundary RG flow by looking at some localized scalar fields. So we just put some localized scalar field as a boundary, at the end of the world brane. This is the effective action, and we can construct explicit solution like this. And this null energy condition is automatically satisfied. It's a boundary entropy monotonically decreasing. And yeah, so we can also talk about rotational invariant case. Then we have two boundary and connected. This kind of, half of this donuts-like shape is also possible by thinking about non-trivial RG flow. Also, finally, I just want to mention if there is some also solution with two boundaries. So it is interesting to think about this cylinder, a cylinder, but with two boundary conditions. But if we assume these two boundary conditions are different, then what happens? This is not the RG flow, but it's somehow close because these two boundary conditions are different. Both are critical, but different conformally invariant boundary conditions. In that case, we have a non-trivial phase diagram if we take this difference of this boundary condition given by scalar field, we have some phase transition. At zero, this is a temperature, and this is a phase diagram temperature, and this difference of boundary condition, delta phi, asymptotic value of scalar field, there is a critical point actually. So usually we have a Hagedorn transition, right, or Hawking page transition, thermal radius and BTZ, but this region is squeezed and goes to zero. And there is some critical point where geometries just coincide with Poincare ADS. And so we have some this kind of phase transition. And also it is interesting to talk about time evolution by weak rotation. And then what we find that, so basically we have to treat this transition matrix instead of density matrix. These two states are different. But we can calculate this geodesic and sort of entanglement. Then we can see interesting phase transition. Like initially it's a linear T behavior. This is the same as basically Hartmann-Maldacena result, but it's at the critical point we have Poincare phase, then it's a log T behavior, and finally end up with constant. So this much looks like very similar to what people call the entanglement phase transition or measurement in this phase transition. So might be some gravity dual of that, but we have to be careful that this quantity we compute, because these two states are different, so it's not entanglement entropy, but something we call pseudo entropy. Pseudo entropy defined from this transition matrix and compute tau log tau. Tau is no longer Hermitian, so in this quantity in general becomes complex, but in this setup it's real valued. But we have some transition. To get a transition, I think we have to take these two states are different. And then we end up with this one. But this still has some nice holographic formula. So if we take some Euclidean time-dependent background, then this two-state Bull and Ket is different. So minimal surface actually gives not entanglement entropy, but this should end. Okay, so basically these are all of my talk. So I just, this is a summary. So we have talked about strong subjectivity and the boundary. We derive g-theorem from strong subjectivity and its holographic counterpart. And here are some future directions, so higher dimensional version, and also time dependence, and maybe algebraic constellation, also interesting. Also maybe future goal maybe to understand strings from qubit, but this is not so surprising. So we often think this area safety might be related to tensor network, but if you look at tensor network, it's like there are holes, and this looks like cross string, and maybe some interesting connections. But if we cut here, it's like we have a kind of degree of freedom. Okay, so thank you very much. I think I'll stop here.
Questions?
Are there any interesting new ways of saturating SSA in this framework compared to
new
without the end of the world?
Okay. Yeah, I'm not sure, but maybe if we have maybe interesting to think about a case with multiple boundary. Think about, but so far we don't have definite example.
Is the entropic definition of the G function manifestly the same as the partition function definition? Or when you found fixed points?
It's not guaranteed, I think. It's just defined by a constant piece, part of entanglement entropy. So I think at the fixed point, they are equivalent, but in general, it's different.
I wonder if your boundary condition becomes dynamical. So is there any interesting conclusion you can follow?
What do you mean by
dynamical, time-dependent boundary condition?
Yeah, that might give some constraint, anyways, from string subjectivity.
Which kind of?
How much it's increasing and so on. But
is there any concrete?
Yeah, I don't have it's a future problem. Yeah.
Can you elaborate on the strings equal qubit?
Yeah, good question. Yeah, but anyway, this tensor network basically tells us that it's become, this quantum state is constructed by some collection of qubits like entanglement. But it's like open closed duality. So this is an open string viewpoint. But if we go to closed string viewpoint, it looks like this closed string is. You can imagine some lattice gauge theory and do some path integral. Right? There are many brackets. It looks like closed string, and we do that for this tensor network. That's basically.
Yeah, thank you. So your proof, of course, depends on Lorentz invariance. And of course, the concept of C-theorem, G-theorem also depends on Lorentz invariance, I think. But this SSA is more general. You don't need Lorentz invariance.
Yes.
So I wonder if you have any insight into
that's a very
generating
interesting
this
question. But I mean, if we don't have Lorentz invariance, we always need some particular time slice. We cannot boost it.
Yeah.
Then we get usually less tight inequality. Yeah. So still, we can apply that argument to non-relativistic case, but I'm not sure how much it is useful, but maybe it's useful then. I think quite interesting. Thank you very much.
Thanks so much. Maybe use that mic.
So maybe I misunderstood something, but in the case of your BCFT case with the holographic dual, I thought I understood that the G contribution depended on the island contribution.
Sorry,
did I misunderstand? The one where you had the 1 plus T, you had a formula which was showing, you had a formula which went, somewhere you had an island contribution.
This one?
Yeah, but after that, at some point, you computed it in a BCFT and you found an island contribution.
So you can calculate it
right.
for this
so sorry, my question was, there are some situations, of course, where the island doesn't exist, where the surface that dominates is Hartmann-Maldacena surface. And so what happens to the log G term in that situation?
Then I think it becomes more divergent. We get an infrared divergence because this geodesic cannot end on anywhere. So.
But shouldn't this be some universal kind of term from the boundary perspective, that you expect a log G term always? Why then?
But I think for BCFT case, always there is island, because that means we can use mirror method. Mirror method means we have island also here. But I think you are talking about some coupling, I mean, really preparing other 2D gravity here. And that case is not highly different. I think this can be different.
Okay, I think let's thank Tadashi.
Thank you.